Okay, question 9. We're now going to be looking at vector diagrams, vectors and forces, and labelling forces. So the magnitude and direction of a force can be represented by a vector, so we can use an arrow. Figure shows the forces acting. Which diagram shows a pair of forces that will give us zero acceleration? So ultimately we have to balance forces. So we want an arrow going that way and an arrow going that way, and they need to be opposite and equal in size. So let's have a look. A's garbage. We've got 2 going to the right. B looks pretty good to me. Let's just rule out the others. C's garbage. They're both moving to the left. And D, that arrow is bigger than that arrow. It can't be that. So it is B. Going on to the next part. 2 small boats are pulling a much larger ship. The ship is connected to the boats with ropes. The tension T in each of the ropes has a magnitude of 20 kilonewtons. Let's just go and see if we need to change it. No, my answer can be in kilonewtons, so we'll leave it alone. The ropes are at right angles to each other, so that's giving you a clue that we can use Pythagoras' theorem as well. Draw a vector diagram and use it to determine the resultant force. So I've said to you for this, we've said we don't ever draw them bum to bum or head to head, so clearly how they're arranged at the moment is not great. We're going to then go down to there, and we're going to measure that line. But because we're smart cookies, we're also going to use Pythagoras' theorem, c squared equals a squared plus b squared. So c equals the square root of a squared plus b squared. And that'll just give us an accurate measure. So clearly this part we could use a ruler to measure it, and then we're going to double check it with Pythagoras. So here's my neat version of it. So draw a 2 centimetre line down. If you want to scale it up, you can. You can have every 1 centimetre is 2. It's up to you. But 2 centimetres down, 2 centimetres across, and measure that line. Now, I can draw that pretty roughly because I'm then going to use Pythagoras to get it dead accurate anyway. So c equals the square root of a squared plus b squared. So that's 20 squared plus 20 squared. So that's going to be the square root of 800. Put that into a calculator and we get 28.3. Nice easy question there. And the next one looks really tricky, but it's actually quite a nice question. So we've got a wooden block connected to a weight by a string. So there's the string, there's the weight. The surfaces of the table and the wooden block are both rough. The wooden block moves across the table at a constant velocity. So already we know the forces are balanced, so they've got to be equal and opposite. Explain how the forces keep the wooden block moving across the table at a constant velocity. You should refer to all the forces. So we're going to have to talk about the forces in each of these directions, and then we're going to say those are balanced and these are balanced. Done. So let's look at labeling it. So we know we have the weight of the wooden block pulling down there. We have the normal contact force, which that should be the same size. We have friction, opposing motion, and we have tension, or the force due to the weight pulling there. And we know that in each of those directions, they're balanced because it's moving at a constant velocity and the block is not rising into the air or sinking into the table. So we're now just going to break down the vertical forces, then we're going to talk about the horizontal forces, and that's it done. So the horizontal forces, I'll just get rid of this because that's going to get a bit messy. So weight is providing tension in the string, or I could say the weight is providing a force to the right on the wooden block. So this is providing a force to the right on the block. Friction is providing a force to the left of the block. Now we've talked about those. Now we've got to say these forces must be equal and opposite as the block is moving at a constant velocity. All right, or these forces are balanced because it's moving at a constant velocity is what that's saying. That's horizontal done. So vertical, the weight of the block is acting downwards. The normal contact force is acting upwards from the table. These forces must be equal and opposite as the block is not accelerating in a downwards or upwards direction. And that's it. So it looks really complicated, but it's quite a nice question. But students did mess that up quite a lot.